So thank you guys for being here today for this yet another periodic seminar. Today we have a talk by André Pedro. He has been here for a couple of years now, and he will be entertaining us on toward a case study on real-time verification of lightweight Avionic controllers using a technique that is calling RMTL. I will not say the last part of it.
Restricted network temporal logic with durations.
Thank you very
So
much.
thank you very much.
So you will have around 45 minutes to
Okay.
this.
So thank you very much. Hi everyone. Today I will present part of my PhD work. I will start with a brief introduction, and I will introduce the required background, and I will show what I'm doing now for the case study. That case study uses a commercial autopilot that is a Pixel autopilot, and it is open hardware, open source autopilot. So first, the motivation of my work and my thesis is the demand that the real-time industry requires to develop this type of system. To ensure that the systems are reliable and safe, we need to increment the ways that we have to do the verification of that type of systems. So basically, we have real-time system that has inherent timeless properties, and we require techniques that are not so complex and not so easy to do, and apply these techniques as a complementary approach to static and approaches like reductive verification and model shaping. So this is why we need dynamic property verification. Basically, we need to verify temporal and timeless constraints. We need to show how these systems behave, and we need to cover how these systems behave, and basically create a certain set of tools that can be used to verify these systems. And of course, one of the things that are missing are the tools for that type of system. So we only have tools that focus on functional properties, that are properties that are inherent on the functionality of the specific applications, and we don't have any type of framework for real-time systems to do dynamic verification that can be used for this particular type of systems where temporal properties for these systems are required. So basically, for what we need that particular approach. Basically, we can use that for detection of anomalies in real-time systems. We can detect anomalies at runtime, at execution time, and this can be a huge effort for this particular type of systems. We can ensure the durations of the past executions of a particular system, and as I already mentioned, we have a complementary approach that is more lightweight because the coverage of the system is reduced, and for that we have this approach. And basically, it's, as I mentioned, it's a lightweight method that can be used to reduce the burden of the software programmers to mitigate and to verify this type of systems. With that, we can put the stamp verifier. So I will introduce the background. I will start with the specification language for restricted metric temporal logic with durations. I will talk about the synthesis of restricted metric temporal logic with durations, and I will show this particular how to synthesize this type of monitors, and I will show the stable and unstable conditions for monitoring. So first, we have the specification language. So we have three focus here. That's basically on the language, on the automatic monitoring generation that we prove that we need to prove that is sound and of course it's reliable. That is the synthesis mechanism that is done automatically. And we have the monitoring library that supports that tool. So what is RMTLD3? Basically RMTLD3 is a temporal logic, it's a metric temporal logic that is composed by terms and formulas. Formulas are basically composed by propositions, by the inequality condition or relation between terms, where terms are defined here. We have the OR operator, that is the logical operator. We have the negation. We have the until operator, the since operator that I will explain next, and we have the existential quantification over formulas of this type. The terms can be constant, that is a constant, it's a value, can be a logical variable, can be one of these terms that we does not focus here into detail, that type of terms. These can be one of the plus or times operation, and we have here the duration of a formula. So the term can compose inequalities, polynomial inequalities, over durations of formulas. We have for that, as common in temporal logics, the eventual and always abbreviations, and basically this is the syntax of the language that we use to specify the system. So, to understand better what is the duration, what the duration term do, we have here a trace, the raw trace, and we have a set of events. We have the epsilon beta, the epsilon alpha, and the epsilon alpha. These three events can be triggered as that scheduler shows, and basically if we want to measure the duration of this particular type of event, we need to sum the area of these activation parts. Summing that, we get the graph something like that, where you have here the line that corresponds to the epsilon beta, and you have here the line that corresponds to the epsilon alpha. And if we sum that durations, we get that squared line that represents the formula epsilon alpha and epsilon beta. Basically, the duration of that is the sum of areas of individual events. With that notion, we can reason about the duration of formulas that are basically sums of square areas. Okay, now given the syntax and the intuition behind the specification language, I will show some intuition from the semantics of that language and how to synthesize that to monitors that really execute on real platforms, in that case on embedded systems. First, we can see that type of formula, that is basically a formula that is quantified over a variable x. Then we have an A that implies a B and x less than 10. So basically this is trivially replaced by A implies B, because there exists an X that satisfies that. So we use that type of property. Our logic can be quantified, and these quantifiers can be discarded prior to the execution. So before we synthesize a monitor, we need to ensure that we have a formula that is not quantified existentially or universally, and we need a set of higher order functions for the until and the since operator. So I will show now the intuition behind the until operator. So the until operator is simple. Basically, the until operator says that A occurs, B occurs, and we have here a count that is a temporal count, that is a common temporal operator, that is an until operator, common in temporal logics, where here we have this type of schedule, where we have A and B, and A here is true, that starts at t equals 0 and continues until a certain t time. After that t time that is less than 12 time units, we get the d event. So that d event holds that formula. So A is until B. But if we change that 20 to 21, we have the time t here, and what happens is that basically B does not fall for the remaining time here. So due to that, this formula is evaluated as false. So this is the principal construction to specify temporal order of events or the occurrence of the propositions. Now we need that simplification of that type of logic. That is the first step that we have. After the simplification, we can generate functions, and after that functions, we can generate lambda functions in C++ that we will see later. So basically, reserved mathematical logic with durations is a formula, can contain a formula in first order logic of real numbers if it is free of duration terms, if it does not have minimum and maximum terms, that are the terms that we see previously with minimum of a formula and maximum of a formula, and if you have the temporal operators that are the until operator and the since operator, and we don't have propositions. Assuming that we can simplify any area MTLD formula, and I will try to exemplify briefly. All these can work. So supposing that you have a formula that starts with an x, x is a logical variable. It's a variable that can be assigned any value between 0 and plus infinity. And here we have inequality or the duration operator, and here we have the duration that is measured for that particular interval, and here we have the formula to calculate that duration. So first we need to replace that duration that is here with a logical variable y. this particular formula hold. So in that case, we replace that new duration as the same step before. We replace that by the variable z and continue along that. With that expression, after that, we have that expression that we can apply the cylindrical algebra decomposition. Applying that cylindrical algebra decomposition, we can get a decomposition in regions and geometric regions of this type of formula. Based on that, we found that this expression for x in -1 and 0, and we find that formula for x in 0 and 10. So given that information, we can say that the existence or modification of that formula is true because there is a possible x if this and this holds, and the universality quantification of this formula is false because we don't have over x, we don't have the full domain. So after obtaining that formula, we replace that we replace the introduced logical variables by this duration factor, and we get this expression. And obviously, as I said before, it is false if x is not in this interval and in this interval. So we have the universal quantification over x false, and we have the existence of quantification over x that is a logical variable true. So the problem here is when you try to simplify something like that, for all x, this interval implies that formula. In that case, due to the usage of an x in the interval of the durations, that is the most complex formula of this type, we can replace that x with a constant. That is much more easier. But assuming that you have x here and you have x here, we will get something like that, applying the simplification algorithm that I showed step by step before. And basically, we have two options to realize that. First is to replace that x finitely many times. That's if we use the real domain, it's impossible. But it's possible if you use a small x and if that x is a natural number. So this step is not good enough for our proof. But you can use the computation of the formula, and you can put that logical variables in the unitary synthesis algorithm. So basically, this is not covered here, and we will address that for the next step over the iteration in our synthesization algorithm. So, to understand better what is the synthesization algorithm, it's basically a set of functions. We call that lambda functions. And basically we define a function with that symbol. And that function here that has these parameters is defined into segments. First, if a is greater than 0, then this is evaluated, and otherwise we get the bottom of R that basically is an element of the set that we can return over 3-valued type. So based on that, we have that function. With that function, we evaluate that other function that is is defined here, where here we have the formal type of that function that basically receives a model that is composed of biological environment and a trace where the trace or the sequence is key. And basically you apply another higher order function fold over that lambda function defined here that parentheses, and of course we could evaluate that as the indicator function. That indicator function basically is 1 or 0 if this computation is true, or if it is false, it is 0. It's not so easy to see clearly that behavior, but what we make here is basically a calculation of an area, basically evaluating a formula, the truth value of a formula. So basically is what we have here. For the computation of the until operator, that is the behavior of the temporal operator that I showed before, we follow the same mechanism. We define the map function over 3 value sets. With that function that has this type, we need to evaluate the other eval fold function that is defined here. And after that, we need another function that is defined here, where the branches of until that is this formula is until this formula. That basically we evaluate this formula and we evaluate the right part of the until formula. And after that, we have this function to select the truth value of this evaluation here. It's not so easy to think in that way, but this is formally described. And basically we can implement that in any functional language, and we can implement that even in C++ and other functions easily, because it's only a map of that into C++. Okay, removing that ugly part, we need to understand why we choose that way to do the things. First, we are aware that automata-based approach, or even using functions, lambda functions to synthesize the logic, we can use automata as a model for the synthesization. This is a common procedure in runtime verification. But for our case, because the inherent behavior of durations, dealing with automatas that are extended with a particular type of clocks, that in this case we call it stopwatches, represents an undecidable reachability problem, or in that case a model undecidable model shaping problem for this particular type of automata. So in that way, we maybe does not get anything better if we choose that particular type of model. Instead of it, due to the explicit time and due to the durations, maybe we can get huge monitors, and monitors that is skewed, that takes more resources and takes more time to execute. And based on that, we think we don't have any proved synthesis, or we don't have any case where you can show explicitly if this is true or not. I'm trying, and we try to discuss that and try to see how the people think about that choose. And at this time, we don't have a clear answer about the usage of automated models for this particular type of durations. So we believe that the use of functions and the use of lambda functions can be a plus for this type of approach, because we can reason as a functional programming paradigm. So we evaluate this synthesization mechanism that we showed before, that is ugly, and what we found is basically that our monitoring approach is polynomial time. So the time complexity is polynomial. That is the expected complexity for this case. For that, we have generated randomly formulas. These formulas can contain durations or temporal operators. I won't enter into much detail in this particular type of graph, but what we conclude from that it is to evaluate a symbol, an event or proposition. We need, in average, 400 nanoseconds in the experiments that we'll perform by the simulation results that running in a common machine, in that particular machine that is not so powerful. And we get for each event an average of 400 nanoseconds to process.
Is the meaning of 6?
The meaning of 6 is in the end of the presentation. It's a reference. It's a reference for the paper, only for the context when the presentation is in other place. Okay, so we need to reason more about the stability of the monitors. Now we have a manner to synthesize monitors. So we have a manner to, from a formal specification, you get a program, an application that do what is supposed to do. And given that, we have encoded that in a functional programming language, in that case in a common programming language, and we evaluate that with simulations. After evaluating that with simulations, we found that we need to take care about the execution of that monitor. So we have functions that execute, and we need to bound that functions that are executing. So for that, we previously proposed 3 conditions. The first condition says that, okay, I have a monitor. The monitor has x, a variable x that has x iterations. So we can see each call of a function as an iterator or a cycle. And with that, we can define this type of bound. We can define another type of bound that is basically you assign a certain amount of time, and this monitor is good until this certain amount of time. Or we can say that if a monitor consumes a symbol, it's okay, and we need to wait for the next iteration to evaluate next symbol. But these conditions are unstable in the sense that the these both conditions, 1 and 2, requires dynamic time execution. So the execution time of the monitors will be not fixed, and this will be an issue when we try to monitor safety properties of real-time systems. So we need to find another way or another hierarchy to construct the monitors, and we think that if we found a monitor that is good in constant time, and given that we turn on that monitor and we can reproduce some other monitors that can be more heavy at execution time, and because of this main monitor that is good in constant time, we can ensure guarantees of duration of the child monitors. And of course, the child monitors can ensure duration properties over the application. In our case, we assume that monitors are always inferring. So a monitor is nothing that stays there for only do a monitorization purpose, like a log. We do not infer that in that particular purpose, but we assume that a monitor is always interfering in a system. So if we think in real-time systems, a monitor can be seen as the main application to ensure guarantees for the slave application, and in that sense, if we have this well-behaved monitor that is good in constant time, we can ensure with other current techniques the durations or the response time, whatever, of the slave applications. So we believe that maybe this is the way to follow for embedded systems on. Okay, now I need to present the case study in more detail. Here it's not so ugly because we will have a demo where I will show how the tool works and what the tool synthesize from this diagram. So for the experiments we have a platform which chooses the pixel that basically has a Cortex M4 processor. This platform it's probably the best autopilot for lightweight drones that is in the market. It's completely open source and open hardware. There are two farmers that may be used in this particular platform. One developed in Switzerland by the PX4 community, and another developed by the open source community that is called Arduino, that came from an Arduino, an idea of picking an autopilot for an Arduino, and we have two possible uses for that model. This board is supplied by 3DR, that is an Australian company that has some state-of-the-art drones, and everything that they produce are normally open source and open hardware. So we think that this is the most realistic scenario to apply that ugly things that I showed before, if you can say that, or you can say that you have a lot of complexity to achieve a small spot, but we does not agree with that. We need some rigor and we need some rules, and we need to get the things step by step. Because only if we get that thing step by step, we can get a real application that works and does not have bugs and does not have unintentional behaviors. So we think that this platform is a realistic case study because we have daily a lot of drones flying in our heads. We have in concerts, we have in every place, and this will be worse in the next years. So we think that applying static analysis or static verification approaches for that type of systems that are lightweight cannot be the best solution because are too complex, and due to the inherent properties of real-time systems can be impossible to do that type of verification in a near future. And maybe we can realize the coverage, and with that we can gain some dependability for this type of systems. So we think that this is the correct platform to follow at the present time. Okay, now here I have some ideas that we have already discussed in our lab. RTML is basically the acronym for Runtime Embedded Monitoring Library. That is a library that was modified from a current library developed by our colleagues. In that case, was proposed by Sebastian Geoffrey this year, and was developed by André. And basically I make some modifications on that library. I remove some things that I don't want, and I put other things that we need for that particular application. We state that we need another particular type of thinking for monitoring approach, because normally people are thinking in monitoring as non-interfering applications. If you need to make some surveillance in one system, you could use monitoring. But if the monitoring does not interfere in the system, the question is what the monitor will do. So it's basically does not doing anything. In that sense, we think that to mitigate issues and to recover that type of issues, we need to interfere in the system. So we have presented a lock and weight-free library that basically uses the exclusive store and exclusive laws of presented in ARM architecture. So this library only works for ARM architecture until now. And we does not override events by default. That is one of the techniques used in the work before. Basically, we could override events in order to get more data. And basically, we generate the buffers and the sizes and the parameters for the buffers using our synthesization tool. That tool basically synthesizes the monitors, synthesizes the interface for the library, and basically puts that in a real-time operating system called NutX and execute in the PixPoc platform. There are three types of possible execution. Until now, we only focus on time-triggered mode. That basically says that the monitor is periodically triggered, but we support the event-based mode as well as a mix of both time and event-based modes. So I will show and demonstrate how the application for the synthesization works. It is constructed in Okama programming language, that is a functional language, and generates code for C++ 11. And the choose to select C++ instead of other programming language that we preferred before. It's because of the implementation of the lambda functions. It's much more easier to map our synthesization approach into C++ lambda functions, because our specification and our evaluate algorithm is defined using lambda functions. So I will show now what it is the tool and what the tool generates. So basically here we have the synthesization program or tool. Basically we have only 500 lines, so we can trust in 500 lines, and we can review that particular lines by hand. And given that, we can reduce these our formulas into C++ lambda functions. We can remove the required pattern matching for this particular type of formulas and reproduce the lambda functions that represents that. And basically we have a configuration file that defines the maximum arrival time for an event, defines the maximum period that is allowed from the library for the monitors. We can instrument what is in C++ the type of the events that we want to synthesize, and we can arrange the monitors by clusters. We call that particular sample as monitor set 1, where we have two formulas that basically we call M simple and M more complex. So here we have a formula that is an OR of a proposition B, that is B OR until of a proposition A and proposition C. And here we have a composition of the damn simple monitors. This is to illustrate that, okay, we specify that, and given that we generate that the file that is in that folder. Monitor set1, we generate these three other files that are common for every monitor that you generate in using that tool. For that, we need to construct some conversions from Boolean, from 3-value sets and 4-value sets. In that case, we have true, false, and unknown, and we have true, false, unknown, and we have the symbol that is used for the iteration. Here we have only the definitions of these conversions. After that, we have a MTLD3 reader that extends in some way the reader presented in the library. For that, we need to define an environment as the semantic of the logic proposes, and we have what is the observation over that set the functions, and we have the ReMTL3 reader that basically uses the reader, the modified reader of the library. Doing that, we synthesize the iteration or the recursive part of our evolution algorithm into iterators. These iterators will iterate over the RMTLD3 reader, and we use that for monitors. So a monitor is defined as simple as that. We define the monitor and simple that contains that we address a buffer and the period of that buffer. That basically we export that buffer for the application. So including that header in any application, we can use that monitor, and we have here the definition of the propositions that are the type of events that we can use in the application. The monitor is an extension of the previous definition of a monitor class in the RTML library, and basically executes that computation function. That computation function here, that is a lambda function, and more complex compute, is a lambda function that encodes the other functions that we have seen before to synthesize that particular type of behavior. This is done completely automatically, and we get here the search over the iterators and the required auxiliary functions for that. So basically, the step here is to convert something like that into C++. This is in a common language, and we can convert that more or less close into C++. And it is basically what we have. We have the configuration file, and we type easily that command will read the configuration file, and will generate that file that I have shown before. And basically, I concluded that my presentation.